Section 9.2 is simplifying square roots. I can simplify radical expressions. We're going to compare the following products. The square root of 4 times the square root of 16. The square root of 4 is 2. The square root of 16 is 4. And when we multiply those together, we get 8. Now, if we'd have taken 4 times 16 first, we'd have gotten 64. And then taken the square root, we still would have gotten 8. So that's going to give us our product property of square roots. We can combine square roots that are being multiplied as one square root and multiply our inside parts. Again, those are called our radicands. We can use the product property of square roots to simplify radical expressions. A radical expression is in simplest form when there's no factors of the expression under the radical sign that have any perfect squares other than 1, and there's no fractions under the radical signs and no radical signs in the denominator of any fraction. In example 1 here, we are going to simplify the radical expression. So here, I'm going to do a factor tree. I have 2 times 90. 90 divided by 2 gives me 45. 45 divided by 2 gives me a decimal, so I'm going to go to 3. 45 divided by 3 gives me 15. And 15 divided by 3 gives me 5. 5 is prime. So another way of writing the square root of 180 is I can rewrite 180 as 2 times 2 times 3 times 3 times 5. And all of my factors are still accounted for. Keep in mind, this is still inside a square root. Now remember that when we take the square root of a number, we are looking for something times itself to get us to that number. So for example, if I take 2 times 2, that gives me 4. Now when I take the square root of 4, I get 2. And that works every time. So what I can do is a little shortcut here. And anytime that I see a pair of values, the same values, I can take that out of my square root as just a 2. Or just a 3. Or just a whatever my factors are. Here I have a pair of 3's. I can take that outside my radical as a 3. And remember, we're multiplying our factors, so we multiply our groups of them that come out as well. And this works again because 2 times 2 is 4. And when I take the square root, remember these are in the square root of 4, I get 2. 3 times 3 is 9. And when I take the square root of 9, I get 3. So here I have 2 times 3, which is 6. And inside my square root, I still have a 5. So that stays there. If we want to check to see if our answer is still equivalent, we can take the square root of 180, which is approximately 13.4, and we can take 6 times the square root of 5, which is also the exact same value, approximately 13.4. So since our approximate values check, it means that there's equivalent expressions. Same idea here in example 2. My first step is going to be to create a factor tree to get my number in prime factor form. So 24 is 2 times 2 times 2 times 3. 2 times 2 times 2 times 3. Don't forget about our s squared though. So times s times s. And that's still inside my square root, so I'm going to write it inside a square root. Now we can look for any pairs of a factor times itself. So 2 times 2 comes out of my radical as a set of 2's, just a 2. 2 doesn't have another factor, 3 doesn't have another factor, but there are a pair of s's. And I can take that out as a group of s's. So here I'm going to have 2 times s, and inside my radical I have everything that didn't have a pair, the 2 times 3, which here is 6. And I know that when we go to check these guys, we can't plug in our s value, but what we can do is we can check our number part. So if I take the square root of 24, I get approximately 4.9. If I take 2 times the square root of 6, I also get approximately 4.9. So my values are the exact same, which means these are equivalent expressions. They're just written a little bit differently, and we have no more perfect squares we can take out. We also could have started off with 24 and divided by perfect squares. We could have checked, does 4 go in there? Yep. And the square root of 4 is 2. and we're left with 6 and try and reduce that way. And with 24, when it's just divisible by 4 as a perfect square, that's pretty easy. But when we're looking at something like 180, we might not think, I bet that's divisible by 36 right away. So if we use the prime factorization method, we're always going to pick out all of our groups as long as we break it completely down to its prime factors. The same relationship exists if we're finding quotients. So I can take the square root of 100 divided by 4, and remember we do whatever's inside our square roots first. That gives me 25. The square root of 25 is 5. I could also take the square root of 100 and divide it by the square root of 4. Square root of 100 is 10, square root of 4 is 2, and when I divide those, I get 5 as well. So it shows our quotient property of square roots, and we can use that to simplify radical expressions as well. So we can either write it as one fraction inside a square root, or we can write it as two separate square roots written in a fraction. And that's going to be helpful here in number 3. We can take the square root of 13 divided by the square root of 36. And remember, we don't want to have a fraction with a square root in the denominator or a denominator in our square root. So I'm going to split these up into 2 pieces, and I'm going to try and simplify. 13 is prime, which means there's no groups we can take out, so it stays as just the square root of 13. 36, however, we can break down. 2 times 18, 2 times 9, and 3 times 3. We also could have done 6 and 6, 9 and 4, whichever factors you want, as long as you break them completely down to their prime factors. 2 is not divisible by anything except 1 and 2. 3 is not divisible by anything except 1 and 2. So here I have 2 times 2 times 3 times 3. Keep in mind that is still inside a square root. We look for any pairs. Here I have a pair of 2's. I can take that out as one set of 2's. And I have a pair of 3's. I can take that out as one set of 3's. I multiply the 3 times 2 and I get 6. And here I have nothing left inside my square root, so I don't even have to write it. What I have left is just a 1. Square root of 1 is 1, and 1 times 6 is just 6. So my final answer is the square root of 13 over 6. And make sure that our simplified pieces stay in the same part of our fraction. So the 13 was in our numerator. It stays in the numerator. Our 6, which is the square root of 36, stays in our denominator. Now, feel free to pause here and give these a try if you'd like. Here we're going to simplify the expression. 63 is 9 times 7, and 9 is 3 times 3. 3 and 7 are prime, so there's nothing else I can do to reduce that. 3 times 3 times 7. I'm going to rewrite my value here, 63, in terms of its prime factors. Keep in mind, though, we're still taking the square root of 63, so I'm going to take the square root of 3 times 3 times 7. When I look here, I have a pair of 3's. I can take that out as a set. And again, 3 times 3 is 9. When I take the square root of 9, I just have 3. So when it comes out, it's just a 3. And now I've used those 3's. So I have a 3 on the outside. Inside my square root, I still have a 7 that didn't have a pair. So 3 square root of 7 is my answer. 54 is 9 times 6, which is 3 times 3, and 2 times 3. So when I write these factors out, I'm going to have 2 times 3 times 3 times 3. Keep in mind, though, I also have t's here, and it's inside a square root. Now I'm going to be looking for any pairs. I have a pair of 3's. Those can come out as a set of 3's, and now I've used them. I have 2 t's. Those can come out as a set of t's, and now I've used them. So on the outside, I multiply together my 3 and my t, and I keep my square root, and I have a 2 and a 3 left that I haven't used yet. So I multiply those together and get 6. Example 3 here. I'm going to split this up and take the square root of 15 divided by the square root of 16. Remember, anytime we have a fraction in a square root, we can split it up and make it the square root of a fraction of 2 square roots instead of a fraction in a square root. 15, I can break into 3 and 5. So I have 3 times 5 inside my square root. I have nothing that can come out as a pair, so I keep my 3 and 5 inside, multiply them together, and I just keep the square root of 15. There's no perfect squares I can take out of there, no groups that come out. 16, however, I can break down. 4 times 4 or 2 times 8, doesn't matter, as long as we get to a simplified form, factored form, of 2 times 2 times 2 times 2. Keep in mind, that's still inside our radical. So we keep it inside our square root. We look here, group of 2's, I can take that out. Another group of 2's, I can take that out. And since we're multiplying our factors, we multiply our sets as well. And 2 times 2 is going to give me 4. Inside my square root, I don't have anything left, just a 1, and we don't need that. So in my denominator, the square root of 16 is just 4. And since the square root of 16 was in my denominator, the 4 stays in my denominator. Number 4 here, I'm going to take the square root of 32 over the square root of n squared. Because they're both inside my square root right now, I give them both a square root. 32 I can break down, 8 times 4. 8 is 4 times 2, and 4 is 2 times 2. 4 is also 2 times 2. So again, we're only including the things at the end of our branches. 2, 2, 2, 2, 2. 2 times itself 5 times. And that's still inside my square root here. I take out any groups that I can. I have a group of 2's that comes out as a 2. I have another group of 2's that comes out as a 2. And I multiply them together. 2 times 2 is 4, and now those are used. Inside my square root, however, I still have a 2. That 2 stays inside my square root. So I have 4 times the square root of 2. Now I can simplify my denominator. N squared is just n times n inside a square root. I can take out a group of n's as an n. I keep my n, and inside my square root, I don't have anything left except a 1. We don't have the 1 shown, but remember, we can always multiply by 1. So all I have in my denominator is n. And again, that stays in my denominator since my n squared was in the denominator. When I take the square root, my result stays in the denominator as well. And that's all I have for you for section 9.2.